This is lecture 8 on urban transportation planning. We will continue our discussion on conceptual aspects in this lecture 2 and hopefully complete our discussion on all aspects related to the concepts. You may recall that we have completed our discussion on problem definition aspect in systems engineering process through the previous 2 lectures. In the last lecture, we discussed about the 5 important components of problem definition phase, starting from constraints, inputs, outputs, value function and decision criterion. Finally, we saw the interconnectivity between all the 6 components in the problem definition phase. Since it is a very important first step in the planning process, let us try to reinforce our ideas about all the components in the problem definition phase by recollecting the definition of the important terms that we saw in the previous class. You may remember, first we discussed about constraints. What is the definition of constraints? Just constraints can be defined as those characteristics of the environment that limit the extent of feasible solution. And the definition of inputs. Input in simple terms is nothing but the demand for the transportation system, which will be derived from the socio-economic characteristics of the urban dwellers. But if you want to precisely define inputs in the context of systems engineering process, we can define inputs as those characteristics of the environment that a system must transform into outputs in the light of the system objectives. Then the term outputs. Outputs, as you may recall, are nothing but the characteristics of the system that we plan for the urban area, like speed, level of safety, cost implication and so on. But in the context of engineering process, we can define outputs in very general term as those characteristics of a system that influence the environment directly and that are a function of the system inputs and the system properties. And then we discussed about value function. In very simple terms, you can recollect value function to be a simple analytical tool to assign money value for different types of outputs of a system, isn't it? And if you want to define the term value function in a systematic way, we can define it as a procedure or analytical tool for mapping the magnitude of an output variable into the units of value in which the objectives are measured. And then decision criterion. As the name implies, we must have some criterion to choose the optimal system among the various alternatives we develop at the end of the planning process. Hence, we can define decision criterion as a rule that instructs the system planner how the individual measures of values associated with the system outputs and the financial resources required for the construction and operation of the system should be manipulated or compared or matched in order to arrive at a single index of value like benefit cost ratio and so on for the system to identify the optimal system. And of course, this is the interconnectivity between the different components which we have seen in the previous class. As you could see, there are 3 components emanating directly from socio-economic environment, and the 4th component, outputs, is derived from the system, and output gets input from the constraints, then value function is derived from the outputs, and then value functions are connected to the objectives, and finally we have the last step as decision criterion. Let us now look at the problem definition phase in a lay person's point of view. What do we really mean by problem definition? Before we answer this question, we should understand what exactly is the problem. What is the problem? The problem is nothing but planning for a transportation system to meet the future transportation requirements of an urban community. That is the problem, and this is a very general problem statement, and unless we add clarity to this statement, we will not be able to proceed with, or the planner will not be able to proceed with the planning process. That is what we do through problem definition process. Let us first pose a general question as follows: what is the minimum level of service of transport system desired by the urban community to improve their quality of life in the future? The overall objective of community is to improve their quality of life in the future. That is the expected goal of any urban community. So if we can answer this question in very simple terms, probably we can understand the 3 important terms related to problem definition phase, namely goal, objective and standard. So what kind of a system they expect to improve their quality of life? Let us say the answers, simple answers are like this. First, they want to see that the journey speed by public transport to be not less than 25 kilometers per hour. We would like to have a public transport system wherein at least we are able to move at the rate of 25 kilometers per hour. That is the desire of the urban community. And next related desire could be the frequency of service of public transport on any route to be not less than 3 per hour. At least there should be 3 bus services or 3 train services per hour on any route. Another important desire of the urban community. And third, there should not be a problem with occupancy in public transit vehicles. The capacity should not be exceeded. Everyone should be able to get into the vehicle whenever they want to travel by transit vehicles. All these statements reflect the desire of the urban community. How do we get these statements? These statements are nothing but the standards about which we have already discussed in detail. Standards are derived from objective. Objectives are based on the community goal, right? So that is how we need to understand the terms goal, objective and standard. Just answering a simple question related to the desire of the urban community to improve their quality of life in the future. Next, let us look at this question: what are the constraints in achieving the desired level of service of transport system in the future? They have clearly stated the desired level of transport system. Is it possible to achieve that level of service? Are there constraints? If there are constraints, that should be known, right? The possible constraints, as we discussed, are financial constraints. If this aspect is made clear, as stated here, the total possible investment for augmentation of transport infrastructure will be about Indian rupees 200 billion or US dollars 5 billion in the horizon year. That is a possible investment from all sources. So, this is a financial constraint. If this constraint is known to the planner, planner can definitely orient the planning process in such a way that this constraint is also taken care of. Other constraint, as we discussed earlier, could be political in nature. They might say that maximum possible subsidy to public transport services, whether train or bus, will be about Indian rupees 20 billion per annum. That is the maximum possible subsidy the government can provide. So, if this information is available to the planner, then this constraint can be put into the planning process and while analyzing the system characteristics, understanding the cost implication of transit system after taking into account the subsidy aspect. So, all these statements are related to the component constraint in problem definition phase, is not it? Next, let us put forth this question: what are the factors that may influence the future demand for transportation in the urban area? Why we are concerned about these factors? Because the planner should know what is the total travel demand in the horizon year or in the future for which the system has to be planned. To quantify the travel demand, we should understand the factors that influence the demand for transportation and how these factors are going to change compared to today's situation. To answer this question, the planner should be clearly informed that there is going to be population growth in that particular urban area. You may wonder why this should be given as an input. Is it not understood? Please understand, there are cities around the world where population is decreasing. So, this is a very important statement. In a particular city, there is going to be population growth and decrease of household size. Household size is decreasing. Increase of household income, increase of household vehicle ownership, and possible increase of per capita trip rate. So, this should be given as input to quantify the total travel demand in the future scenario. All these things are related to which component in the problem definition phase? Inputs, right? Inputs are nothing but the demand generated by the socio-economic characteristics of the urban dwellers. So, once you are able to answer the question, you understand the definition and implication of the component inputs. Let us put this question to us: what are the quality aspects of transport system that may influence the future demand? This question is related to which component? Obviously, outputs of the system. Try to provide answer for this question. Maybe speed of travel might influence the demand for transportation very significantly in the future. Then travel cost, level of safety, level of comfort, and so on. So, the planner should get this idea very clearly. So, these are all the factors that he or she will consider to quantify the service provided by a particular system. That is the idea of listing these aspects as answer for this particular question. Then, how to assess the quality of future transport system? Is there a way to assess the quality or estimate or quantify the quality of service provided by a particular transport system. How do we do that? The answer is this: estimate money value of the relevant system outputs like speed, level of safety and so on using appropriate functional forms. Isn't it? That is the only way to answer this question, and this question and answer are related to which component? Value function in the problem definition phase. And then the last question, how to choose the system that will provide better quality of service. When we have several alternatives, how do we choose the system which will provide better quality of service? How to decide? Obviously this question is related to decision criterion. What is the criterion? Use benefit cost analysis and stated preference approach to choose the optimal system. Combine both, use ranking and weighting procedure and get a common base for comparison of various alternatives to choose the optimal one. So this is how I would like you to understand the process of problem definition. If this information is provided to the planner beforehand, then he or she is very clear as to how to proceed with the planning process. That is the idea of defining the problem with all the 6 important components. So with this understanding, let us go further in the systems engineering process. You can realize now that we have completed our discussion on the details listed in the first 2 boxes only so far, and the next step is solution generation, then solution analysis, evaluation and choice, recommended strategy and implementation. So what do we mean by solution generation? As the term implies, it is nothing but generation of different alternative solutions to the transportation problem. The aim of this phase is to generate an array of solutions that satisfies the previously established objectives. That is very important, should satisfy the established objectives, the requirement of the urban community to a lesser or greater degree depending upon the system that we choose as an alternative, to a lesser or greater degree, and which does not violate the constraints, very important aspect, does not violate the constraints. Planner should not propose an alternative which violates a constraint, there is no use. It cannot be considered as an alternative because it is violating the constraint. Then solution analysis. Why solution analysis? We have to compare the alternatives. Unless we analyze the merits and demerits of each alternative in detail, we will not be able to compare. So that is the idea of analyzing the solution. Solution analysis. The objective of this step is to predict the probable operating state in terms of speed, comfort, right, cost and so on, probable operating state of each of the alternative systems, right, generated in the previous phase given expectations about the state of the environment, state of the socio-economic characteristics and land use pattern at the in the horizon year, right. And this is normally done through a systematic analytical procedure. In urban transportation planning, the input magnitudes and the behavior of alternative systems are estimated. What is the input magnitude? The demand for transportation inputs, right, and the behavior of alternatives is nothing but study of the characteristics of the different alternative systems, how they behave in terms of speed, cost and so on, right, are estimated normally through the use of a 4-phase process consisting of trip generation analysis, modal split analysis, trip distribution analysis, and traffic assignment analysis. In fact, we will be spending quite some time later on each of these 4 important steps. This is just an indication of what we are going to do in the following classes. Then evaluation and choice. We need to evaluate each of the alternatives and choose the optimal one. The aim of this step is to identify the alternative system that satisfies the objectives to the greatest extent, maximum possible extent. The data required for this step are the output variable magnitudes predicted in the system analysis step, the value function, and the decision criterion. All these things will go as input in the evaluation and choice process identified in the problem definition step. And finally, implementation with some particular strategy. And the optimum system for the horizon year is identified in the previous phase, and the aim of this phase is to formulate a strategy for implementing the chosen system throughout the planning period. That is what I said earlier. Strategy is normally phasing the project implementation, implementing the projects in phases, so that it goes on throughout the planning period. We fix targets, what should be completed on 5th year, 10th year, 15th year, 20th year, and so on, and carry out the development as per the planned strategy. So this covers all aspects related to the systems engineering process. Let us have a check whether we have covered all listed aspects. Now we know clearly what do we mean by each of these steps in the systems engineering process, which can be directly applied for transportation systems planning process, right. Now what do we mean by an urban area? There are some definitions given by the Population Census Department of Government of India. These just are given to you as general information. It is not very specific to this particular course. And population of an urban area should not be less than 5,000. So to qualify as an urban area, the total population should be at least 5,000. Could be a small town. Then non-agricultural workers, not less than 75% of the total workers. Census records have the record of total workers in the whole of the population, right. Total workers might constitute about say 30% of the whole of the population. And for a particular area to be qualified as urban area, the workers involved in agricultural operation should not be more than 25%. Okay, that is the condition to qualify a particular area as an urban area. Population density not less than 400 per square kilometer, right. It should be dense. If there is a very sparse development, scattered development, then you cannot really call such areas as urban areas. There should be reasonable density of development. And towns with population of 0.1 million and above are termed as cities. Often we just interchange the terms towns and cities, but they say if the population is more than 0.1 million, such urban areas can be termed as cities, and other smaller urban areas could be termed as towns. So this is the guideline given by the census department. Now let us get back to the problem of quantifying the demand for transportation in the horizon year, which will form the input for the problem definition phase. How do we quantify the demand for transportation in the future year? We must have some framework. For example, if you want to analyze the demand at the micro level, we should understand that trips made by urban travelers emanate at home. From home they travel to different places and come back in the evening, right. In certain cases trips might emanate from workplaces, shopping areas, recreation centers and so on. If you wish to analyze trips generated by each of the household, each of the residential building in an urban area, there could be millions of buildings in large urban areas, and if we collect data about the trips made by each of the households, then it will be a highly complex data set which is not that easily analyzed and behavior of travel pattern understood. There is no need also to go to that micro level to plan for transportation system for an urban area. We can always think of aggregating the points of trip generation and trip attraction, so that we have a manageable amount of data base which can be analyzed with clear understanding, the results of which can be used to plan for the appropriate transportation system. How to aggregate and analyze the travel pattern? Any suggestion? Instead of considering each household as point of origin or destination, why not just earmark a small area of more or less similar type of land use of radius, say about 1 kilometer radius or 1.5 kilometers, even 2 kilometers, depending upon the homogeneity of the land use, and consider that smaller area as a single unit and quantify the total trips produced or attracted by that area. Similarly, divide the entire urban space into smaller land use parcels and treat each of these land use parcels as points of trip generation. Would it work? For example, let us say we are planning for the transportation system for this city. Ultimately, at the end of the planning process, what is that we are going to propose? We are going to propose augmentation for the existing transportation infrastructure in the form of widening of roads, construction of grade separation facilities, construction of transport terminals, or introduction of new transport services and so on. All these things need not take into account what is happening on IIT campus. All the trips emanating from this campus is joining the mainstream at one point or at few points, isn't it? So our concern is about the major links of the transportation network. If we consider the road network, we are concerned about arterial roads, sub-arterial and maybe expressways if we have some. We are not very much concerned in the planning process about the minor roads which extend to connect the local communities. That will automatically emanate. So keeping this in mind, it is possible to divide the entire urban area into compact land use parcels with homogeneous land use and fix a point for each of these areas as points of trip origin and trip destination. Unless we do that, we will not be able to create a manageable database for the planning process, right. As a first step, we need to delineate the urban space, fix a boundary for our study area. This boundary normally extends beyond the municipal boundary of any town or city, because normally people living in peripheral areas might also travel on a regular basis, daily basis into the city and go back home. So, you must study the travel pattern very carefully and cover all the points of origin and destination which contribute for the regular travel pattern on daily basis in the urban area. That should be the basis for fixing the boundary. This is what I meant, urban area boundary, and then divide the area into smaller parts. We will discuss in detail later in transportation survey on what basis to divide urban areas into smaller land use parcels. As of now, you can assume that it is possible to divide the urban area into smaller land use parcels based on certain conditions, right. And then we call these land use parcels as land use parcel or traffic zone, because we are going to assume that traffic is going to be generated from these smaller land use parcels. And another important aspect is fix one single point for each of these small land use parcels, which is assumed to be the trip generating point. We are going to assume that all the trips, if there are 5,000 trips generated from this campus, we are going to assume that all the 5,000 trips are generated from Gajendra circle only, no, and from nowhere else. Okay. This is the approximation we are going to make, which may not affect our overall calculation at the macro level. That is what is meant by fixing the centroids for each of the land use parcels. Of course, this is what we call as zone centroid. Then analysis of travel pattern is easier. What we are going to do from now on is just to study the movement pattern, mobility pattern between all these identified points. Okay, point 1 to all other points, point 2 to all other points, and so on, right. So, that way it will be easy for us to understand the travel pattern and analyze the total transportation demand. This is the first important step. And then once we accept this process, then we get into the analysis phase, and the analysis phase involves, as I mentioned, 4 important steps: trip generation analysis, modal split analysis, trip distribution analysis, and traffic assignment analysis. And there are other steps involved which are quite closely related to these 4 steps. Let us take an overview of the whole of the analytical process, including the data collection process, in the form of a flow chart. This flow chart gives you a complete picture of data collection, analysis, and travel demand prediction for the horizon year. I have divided the analysis into 2 parts. One part pertains to base year condition. The other part shown on the right hand side pertains to horizon year condition. And interconnectivity between the steps are shown by arrows. Let us first look at the different steps pertaining to base year condition. The first important step is land use survey. We know what are the categories of urban land uses. We must collect data with regard to type and intensity of use in each type of the land use over the entire urban area. That data should be collected. Then travel survey. We must have all the information related to travel pattern of the urban dwellers. This includes the related traffic surveys also concerning the way, the vehicles, the actual traffic experienced, the terminals, the fleet size of transit system, and so on. All the information will be collected while we do travel survey. Then this will go as input to the 4 important analytical steps, namely trip generation, modeling, then model split is split into 2 stages: captive model split model, choice model split models, then trip distribution models, route assignment, then check against measured volumes. We will just briefly look at the procedure involved in each of these 4 major analytical steps. What exactly we are going to do in trip generation analysis? Trip generation has got 2 aspects: trip production and trip attraction. Later we will discuss in detail about these 2 aspects. Trip production and attraction are related to estimation of the trips produced and attracted by each of the traffic zones that we have identified earlier. This is zone wise estimation of the total trip production and attraction. We are not going to do anything about mobility or movement from one point to another. This exercise is concerned with quantifying the total trip ends produced, trip ends attracted zone wise. Okay, we will have some number of total of trips produced and trips attracted for each of the zones. How do we do that? We will just try to relate the trip production with the set of causal factors, trip attraction with a set of relevant causal factors. So that is how we get some equation to quantify the trip production and trip attraction. Next, model split. Once you quantify the total trips, we need to know the mode chosen by the travelers at each of the traffic zones. For that, it will be convenient for us first if we segregate the captive travelers. Who are the captive travelers? The travelers who are captive to a particular mode or captive travelers. Let us say there are certain percentage of households with no vehicles, not even bicycle. Then what will be their mode of transportation? What will be their vehicular mode of transportation? Public transit only. So there is no choice available to this section of the travelers. And why include this section in mode choice analysis when they have no choice? So you can segregate that portion of the travelers from your mode choice analysis, and this process is what we call here as captive model split model. It is not really modeling, it is a simple analytical procedure of segregating captive travelers from the whole of the travelers. Then we will have data pertaining to choice travelers only, who have real choice. Then develop a model to understand the mode choice process. Identify the factors that will influence choice of mode by travelers. Then just develop an equation which will give an idea about the probability of choice of a particular mode by a particular type of traveler, and use this equation to get the actual mode choice at each of the traffic zones we have identified already. In the previous step we have estimated the total trip production and attraction. After completion of mode choice analysis, we will know out of the total how many or what percentage will take transit, what percentage will take motorized two-wheeler, what percentage will take car, what percentage will go by foot. All the information will be available, again zone wise. That is what we will be doing in mode choice analysis. Then trip distribution. Now we look at the interchange of trips between the zone centroids, the points that we have already fixed, and try to identify first the factors that will influence the trip distribution. What are the possible factors that might influence the distribution of trips? How people travel from one zone to another zone. One possibility is their home is located in one zone, workplace is in another zone, so they have to travel to that zone to go to work. Or if there are children going to school, school might be located in a different zone, they travel to a different zone. A shopping mall may be available in some other zone, they travel from one zone to another zone. So, identify the causal factors, trip purpose as well as other related issues. Normally, when the distance of travel involved from a particular zone is more, as the distance increases, number of trips exchanged will be decreasing, isn't it? Normally, urban dwellers would like to minimize the intensity of travel to attend to different activities. The general trend is more is the distance, less is the trip interchange between zonal pairs. So, all this information will be analyzed and we will develop a model to explain the trip distribution process, right. So, we will distribute the trips as percent trips, not in terms of vehicular trips. Even in trip distribution process, we distribute the trips as percent trips. So, we can distribute the trips using an analytical technique and then cross check with the data that we will be collecting during the base year condition. Then in the fourth step, which is route assignment, we actually convert the percent trips into equivalent vehicular trips. Why? That is what we observe in the field, that is what is happening actually in the field. People travel using different modes. You cannot just model everybody traveling or walking on a road, that is not the reality. So, we have to really convert the percent trips into vehicular trips first, and then if you consider a zonal pair, zone 10 and 11, there could be several alternative routes available to go from 1 to 11, and different people might be taking different alternative routes. So, we must understand the choice of route by the traveller. There will be some factor influencing the choice of route. We must identify the factor and then try to develop an equation or model to explain the route choice process. And then the converted vehicular traffic has to be assigned along various routes based on our calculation. Once you do that, you are actually reproducing the actual traffic flow by theoretical means. We started with quantifying the total trip production and trip attraction at the zonal level, then understanding the choice of mode, then understanding the distribution of trips on space initially between zone centroids, then assigning route for these trips after converting the trips into equivalent vehicular trips. Once you do this exercise, if you know the road geometry of the entire road network on each link, then you will be able to visualize theoretically what will be the traffic volume over the entire road network, isn't it? After traffic assignment, you should get information about traffic volume as well as composition. Another important aspect to be kept in mind in traffic assignment is that assignment of traffic by transit is easier, because transit service is operated on fixed routes. So, once you know the origin and destination of the passengers, you can easily understand the route which will be taken by the traveller, and you can put all these kinds of travellers into that particular route. So, transit assignment is simpler and assignment is more complex in the case of private or personal vehicle users. Assignment has to be done in detail only for personal vehicle users. Transit use is quite simple because route is already fixed. Okay. Once you assign the personal vehicles on the road along with the transit service, maybe bus service, we should be able to visualize the total traffic flow on the road network, or we should know the total traffic volume as well as composition at any point of time in an urban road network. Do you think that it is a possibility? It is possible, provided we take care at every step to see that your theoretical model is valid. You can cross check statistically, logically and so on, and ensure that at every stage your equation or model is reproducing the reality. Trip production, right, mode choice, trip distribution, then route assignment. And once you are able to theoretically reproduce the actual traffic flow, you have the advantage of comparing the theoretically predicted traffic flow with the actual observed traffic flow for the base year condition. We are talking about base year analysis only, isn't it? You have the traffic flow information in the base year over the entire transportation network. You can measure the traffic volume and composition. Now you are theoretically estimating the same. Compare your estimated traffic volume and composition on each of the links which were field observed values. If the two values are matching, you can be happy and your model is perfect. If not, you have to go back, work back and look for possible errors, correct wherever required and then rework on the 4 steps and get again the revised traffic volume, compare with the actual traffic volume and iteratively do this exercise until there is a reasonable match between theoretically estimated traffic volume and field observed traffic volume. If it is matching, then your model is able to explain the reality to a reasonable extent. Why exerting ourselves to develop this kind of model? What is the purpose? So we can as well measure trip production, mode choice, isn't it, trip distribution and route assignment for base year condition. Once you fix a zone boundary, you can just actually conduct surveys and get the trip production value, trip attraction value and so on. Why should you develop a model? Because, yes please.
We are planning for the future, we are not planning for the base.
Yes, so we need to have some tool to predict the future trip production, future trip attraction, future mode choice, future trip distribution and future traffic assignment. That is the ultimate objective. That is why we are interested to explain what is happening today theoretically, so that these theoretical models can be used to predict the future scenario as accurately as possible. That is what is shown on the right hand side. What we do for the horizon year, we predict the land use allocation, which involves prediction of the population growth, household changes and land use changes, everything together, right. The future urban land use is predicted. There are models available about which we will discuss later to predict the future land use pattern of an urban area. Once you do that, you just use this model, trip generation model, use the land use data and get information about zonal trip ends. Traffic zones will be there for future condition also. If the area is going to expand, you extend your zoning process and fix the points of trip origin and destination. Using the models, you can find out the total trip ends produced and attracted at each of the traffic zones. So once you use this model for the future condition, you get zonal trip ends at all the traffic zones, right. Then use the captive mode choice model and choice mode choice model, and if you are going to introduce new modes, okay, that will come into the choice process. So introduce that also for the horizon year and use your mode choice model to analyze the mode choice process for the horizon year condition and get the trip ends by mode. If you are going to introduce metro rail, you will get another new mode, but still your model is valid to analyze such situations also. It is possible. So you will get trip ends by mode for each of the traffic zones for a horizon year condition. Then use your trip distribution model and understand the OD volumes by mode for horizon year condition, trip distribution for the horizon year condition. Then route assignment can be done directly from the OD volumes, right. There is no input required further for the horizon air condition, and once you assign the route you get volumes by link and mode for the future transportation network. That is what we required. So once you get this volume, we can check whether the available infrastructure is adequate or not. You may have a limited width of road, but after assignment for the horizon air condition you may get double the capacity of the existing roadway. That means definitely you need to widen that particular stretch of road. If it is on a continuous set of links along a route, that is going to be a major traffic corridor. If that is the situation, then you can think of introducing new systems like light rail, metro rail system and so on. It is possible by this process to identify major traffic corridors and decide about the transit system which will suit your future requirement. So this is what we need to understand by the sequence of activities in transport analysis process. With this we have developed some understanding about the problem definition process and the major analytical steps involved in development of demand models to ultimately get the future travel demand and the required augmentation for the transportation infrastructure, right. This is how I would like to summarize today's discussion. In the next class we will discuss about the first important analytical step, namely trip generation analysis. With this we will close our discussion for today.